We talk about sublimation. We've been going over different state changes in this chapter, and here's one that's a little bit odd. So sublimation, this is actually a, my pointer going? Sublimation is a I don't know what word I was starting with there. Transformation, perhaps? Going from a solid state directly to a gas state without melting in between. So this is something that we don't necessarily directly observe very frequently. The opposite of sublimation is called deposition, and that's going from a gas directly to a solid. So how does this work? Well, here we have an illustration of ice. Water in the solid state, you'll notice all these little water molecules are lined up, and they are vibrating, right? Everything has a certain amount of thermal energy. In a solid, the particles are vibrating, they're just not moving relative to each other. And the average kinetic energy of those particles is related to the temperature. It's an average, so some particles have high kinetic energy, they're just that crazy person in class who cannot sit still, right? And other molecules have really low energy. Those are the ones that are falling asleep literally in class. They've got their head down, they're snoring, right? You've got averages, you've got highs and lows within that. Particles with high energy that happen to be near the surface of the solid may be able to escape the intermolecular forces that are holding them together. So there's one particle at a time just escaping completely. It's not melting, it's not forming a liquid, it's just escaping into the gas phase, and that's sublimation. So solid substances also have vapor pressures. Their vapor pressures are much lower than liquids, but they do have vapor pressure because anytime you have a substance like this, like water, in the solid state, you also have some water in the gas state above it. Sublimation usually is going to occur at a faster rate if the container is open and those gas particles can just escape and fly away. If it's in a closed container, the gas molecules are going to bounce into something and then they're going to deposit and go back into the solid state. So some things that we observe in everyday life that are a result of the sublimation of water. Ice cubes left in the freezer slowly shrink. Go home and check way in the back of the freezer. If you have ice cube trays, it's easier to observe. But if you have an ice machine, find those ice cubes that get stuck and never come out. Compare them to the size of the new ice cubes. They're probably smaller. How do ice cubes shrink in the freezer, right? There was actually a great Arthur episode. Remember Arthur? You guys are probably about the age that you watched Arthur when you were little. DW saved a snowball in the freezer, and then she was very upset when it was like so much smaller later. It was subliming in the freezer, okay? So you've got ice in the freezer, and some of the molecules just fly away into the gas state. It's called sublimation. The longer you leave it there, the more it's going to happen. We see that ice crystals grow inside airtight bags of frozen foods. You know, this is an experiment you could do if you're very patient. Buy 2 bags of tater tots. Open one up, cook it, look at it. When you open it and it's fresh, there's probably very few ice crystals in there. Leave the other bag in the back of the freezer for 6 months or a year. Pull it out, dump it on the pan. It's like, who puts ice in a bag of tater tots? This is going to get all soggy when I bake it. Where did all those ice crystals come from? It was water that used to be in your tater tots. You've heard of freezer burn. So you've got this nice piece of steak and you save it for a special occasion. In the freezer, you pull it out and it's like all dry and nasty on the outside, right? We call that freezer burn. Well, how does that happen? Well, the water that's inside the meat, frozen in your freezer, sublimes. It leaves the meat. Your food gets dehydrated gradually, and then it just doesn't taste the same. So how can you reduce that? Here's practical application of chemistry. A deep freeze is a freezer that keeps the temperature significantly lower than a regular freezer. The colder the temperature, the less sublimation occurs. Well, you probably can't just go out and buy a brand new freezer. I certainly couldn't. Another way you can fix this is by sealing the food without any airspace. So this is why people will wrap a piece of meat in foil and scrunch the foil all around it and then pack it in a plastic bag. Because when the foil molds to the meat, then there's very little airspace, so that if it sublimes, it really can't go anywhere. And so you have less of this dehydration of your meat. Or you can get those, sealer bags that suck all the air out. Those work really well too. Any questions about sublimation in the freezer? I think this is interesting. Dry ice. Dry ice sublimes also. Dry ice is actually solid carbon dioxide. They get it from the air. You just pull it out of the air, cool it down. You got solid carbon dioxide. You can buy it at the grocery store, provided you're 18 or older. They keep it locked up. So here's a picture of dry ice. We call it dry ice because it doesn't melt. Regular ice, I guess you could say, is wet ice. You've got a cooler, you put some ice in there, you put some sandwiches in there, and 3 hours later when you go to eat lunch, what's happened? The ice melted, and your sandwiches are soggy. Nasty. The ice made water. Use dry ice, it doesn't melt. It sublimes. So there will be less of your dry ice later, but your sandwiches won't be wet. And that's why they use dry ice when they ship things that have to remain cold, because you don't get any leaking out of the package. And, people in the shipping business get very, very nervous when packages leak. That's not a good thing. So solid carbon dioxide will sublime at room temperature, but it doesn't melt. Okay. So let's talk about fusion. Fusion is just a fancy word for melting. And we talk about heat of fusion, and so we need to know what fusion refers to. So the way I remember this is I think about a bunch of chocolate chips, which, is kind of a happy thought. And if you heat the chocolate chips up, they get soft and squishy, right? And they fuse together into one just giant lump of yummy chocolate, still very edible. Fusion and melting are the same thing, okay? So if we take that block of ice and we warm it up, the molecules vibrate faster, and the more we warm it up, the more they vibrate, right? At some point, they have enough energy to partially overcome the intermolecular forces that are holding them together. So now it's going to melt. It's going to change from a solid into a liquid, where the particles are still touchingly close, but they're moving around relative to each other. So we see a heating curve. We see a heating curve for melting or fusion that looks similar to what we observed for the boiling of water. If we take solid water, ice at like minus 10 degrees, and we heat it up, add heat to it, the temperature rises. We expect that. When we get to 0 degrees Celsius, the ice begins to melt. At that point, the temperature will remain constant until all the ice has melted. Because the heat that's going into it is going into breaking the intermolecular forces and causing the liquid to form. It does not go into increasing the temperature. So we see this flat section here. Once all the ice is melted, then the temperature will go up. This is one of the reasons why 0 degrees Celsius is standard temperature. 0 degrees Celsius is very easy to obtain. All you need is ice and water. Whatever container you have, stick it in an ice water bath, wait a few minutes. You don't even need a thermometer. You can say that's 0 degrees Celsius. Very easy to do. Now I've got my rock star here with ice in it. The temperature of that is 0 degrees Celsius. See, this is a prop for teaching. That's why I have to bring this every day, right? In my periodic table cup. But anytime you have ice and water together, it is at the melting point. Just like anytime you have a liquid and a gas together at its boiling, that's at the boiling point of that liquid. If you add more heat, you make the solid melt faster, but you don't increase the temperature. Melting is an endothermic process. This makes sense. How do you melt an ice cube? You put heat into it, right? Endothermic, going in. So the amount of heat needed is called the heat of fusion. So delta H again, but FUS for fusion. And this is why we need to remember what fusion is. Fusion is melting. Heat required to melt 1 mole of a solid. So 1 mole of solid water going to 1 mole of liquid water is going to require that we put energy in. It requires 6.02 kilojoules per mole. So just like the calculation we did with heat of vaporization, we could calculate, if you had 5 kilograms of ice, how much energy would it require to melt it? We could do that. The opposite of melting is freezing. This is actually one of my favorite multiple choice questions. It just messes with people's minds. Say, what's the opposite of melting? And then you give them some choices, and they do weird things like say boiling. Boiling's not the opposite of melting. Freezing is the opposite of melting. If melting is endothermic, the opposite, freezing, has to be exothermic. That seems weird, doesn't it? Something that's freezing gives off energy? Yeah, that's hard to think about. That's why I think it's better to say to yourself, because this could come up on an exam. Okay, I know that melting is endothermic. If I want that ice cube to melt, I'm going to heat it up. That makes sense to me. So now just say, okay, what's the opposite process is freezing. Then it must be the opposite. It must be exothermic. So freezing is exothermic. Your freezer at home is pumping heat out of the inside. And that's how the water or whatever you put in there freezes. It's because the freezer is sucking the energy out. It's not a spontaneous process there, but it is an exothermic process. So I live in Reedley, which is just surrounded by fruit trees, right? Stone fruit and citrus. In the winter, as is coming up, we have concerns about freezing temperatures at night because you get below about 26 degrees for several hours and the oranges freeze. And that just ruins them completely, and then the farmers in a bad state, and then all the fruit pickers and the packers and everything. It just messes up everything, so we don't want the fruit to freeze. Well, you can't just go put space heaters in your orchard, and you can't cover it with a blanket or anything to keep it from freezing. But what you can do is take advantage of the exothermic process of water freezing. So what they do is they water the fields when a freeze is predicted. So you got lots of water in the field. Standing water is best, but even just if the ground is good and soaking wet, that's okay. The temperature drops. I'm going to switch to Fahrenheit here because that's what makes more sense to us. So as the temperature falls to 32 degrees Fahrenheit, the water in the field begins to freeze. What happens when you have liquid water and solid water together? The temperature stays the same. We looked at the heating curve. You could draw this as a cooling curve. You just reverse it. As you're cooling it down, when you get to the point where it begins to freeze, the temperature remains the same until all of it has frozen. So what happens in the field is as the water freezes, it's releasing some energy and keeping it at the same temperature. And so down there on the ground, you've got 32 degrees Fahrenheit. Now the air above it may get colder, and that's why they have the big turbines, the wind machines. So in Reedley, in the middle of the night, you wake up and you're like, oh yeah, it must be cold. I hear the wind machines, even in town. I mean, they're really loud. It's like a whole bunch of airplanes outside. They blow that air around, and they can keep the oranges from freezing. Because it rarely gets down to 26 degrees. And if you can just keep it at 27, you'll be fine. So they just need this little bit. So I think that's neat. Exothermic freezing of water saves oranges. Any questions? So we have heats of fusion, and we talked earlier about heats of vaporization. Here's a table showing heats of vaporization and fusion in a table form. Obviously, a table showing it in a table form. A bar graph, let's say. So the heat of vaporization is always significantly larger than the heat of fusion. It takes a lot more energy to vaporize something than it does to melt something. When you melt a solid, you only need to partially overcome the intermolecular forces. In order to vaporize it, you need to completely break them, and so that requires a lot more energy. Here's a table that you may need for homework, giving melting points and heats of fusion for some different substances. Those are not numbers that you need to memorize. You would be given those on an exam if you needed them.